myself Dr. Amita Asthana from Akgec Ghaziabad. In this video lecture, we will study the amplitude modulation, and the topic has been taken from BC 101 Fundamentals of Electronics Engineering subject, and this topic belongs to unit number 5. So now coming to the amplitude modulation waveform, first of all we should understand what is a modulating signal, and then we will see the carrier waveform, and then we will see how we are getting the amplitude modulated wave. So here this is my modulating signal. This is my modulating signal. This is one period, and this waveform has been taken as, the masses signal and a very low frequency waveform. As we can see, the time period is very large, so frequency is very less, and this particular waveform cannot be transmitted at all without the modulation process, because this particular waveform, my message signal or the modulating waveform MT, is very low in frequency. A low frequency waveform cannot be transmitted to the longer distances. So what should be the methodology to be adopted so that we can transmit this waveform to higher distances? So what we do is we generate a carrier signal. We generate a carrier signal in which we take the frequency of the carrier signal to be very high, and then we combine these two waveforms, my modulating signal plus the carrier signal, to generate the amplitude modulated wave. So here the second waveform, which I can see in the diagram, that we have taken one very high frequency waveform. We can see the time period of this particular waveform is very low. Okay, so if time period is low, then frequency is very high for this waveform. So we have taken a carrier signal CT, very high frequency is very high, and this is my message signal MT. The frequency is very low. The problem with this waveform is we cannot transmit because it is very low in frequency, so we cannot transmit this particular waveform. This particular waveform can be transmitted. So I will take advantage of this frequency, this very high frequency, to transmit my message signal, which is very low in frequency. So what is the process? What I will do is I will allow my carrier wave to follow the envelope of the modulating signal. Okay, here, but frequency is changed only a bit. Okay, so what I will see that this carrier waveform is adopting the amplitude of the modulating signal and is being transmitted as amplitude modulated wave. Whatever I am making in red pen, this is my amplitude modulated wave. This is my final amplitude modulated okay. This wave is being transmitted. If I can see this wave, then this wave is following the envelope of my message signal, which is this. Okay, from both sides, upper side and lower side both, and the frequency is quite high. Now I can transmit it to the higher distances, because this particular wave is having very high frequency, and it is also following the message signal. What it is carrying? My information. my information of the message signal, because it is following the amplitude of my message signal, and it is also having its very high frequency component, so that it can be transmitted to the higher distances. So I am getting two benefits. My message signal information is lying with this particular waveform, as well as I am utilizing the high frequency speciality of this carrier wave. Okay, in this the carrier wave is following the amplitude of the modulating waveform. That's why I am calling it as amplitude modulation. Now, one thing I can also note from this particular diagram, if I see this particular is my, let's say, AC, and this is my AM. Then this peak is AM plus AC, and this bottom is AC minus, right? Okay, so this point is, this particular distance is AC minus AM, and this particular distance is AC plus AM. So the highest, highest point of this particular waveform is AM plus AC, and the lowest point of this particular waveform is AC minus AM. Let's say I have taken a cosine waveform of message signal. The frequency of the message signal is FM, and the frequency of the carrier signal is FC. The amplitude of the modulating signal or message signal is AM, and the amplitude of the carrier signal is AC. Okay, so here we have taken two sinusoidal signals, and message signal and carrier signal. This is my message signal, and this is my carrier signal. And where AM and AC are the amplitudes of the modulating signal and the carrier signal respectively. FM and FC are the frequency of the modulating signal and the carrier signal respectively. Now the resultant equation, which comes from the amplitude modulation, after this process, when we are doing this, the amplitude modulated wave, the standard equation can be written as AC plus AM cos 2 pi FMT bracket whole bracket cos 2 pi FCT. So this is my standard equation of the amplitude modulated wave, and which is very important. We should always remember this particular equation. If I take AC outside the from the equation, then my equation becomes, amplitude modulated wave equation becomes AC 1 plus AM by AC cos 2 pi FMT cos 2 pi FCT. Now this AM by AC is known as modulation index mu. This is known as modulation index or modulation depth. So here I have mu is equal to AM by AC. So modulation index is the ratio of amplitude of the modulating wave divided by the amplitude of the carrier wave. Now already we have seen the maximum amplitude was AC plus AM, and the minimum amplitude was AC minus AM. So I can from these two equations I can find out AC and I can find out AM. So what I am finding out is AC is A max plus A minimum upon 2, and AM is A max minus A minimum upon 2. And if I want to calculate my modulation index in terms of A max and A minimum, I can find out mu is equal to A maximum minus A minimum upon A maximum plus A minimum. This is how we can write my mu to be equal to, and it is, yes, it is AM by AC again. Okay, this is AM by AC, right? So modulation index can be defined as the ratio of the minimum amplitude of the modulated wave upon maximum amplitude of the modulated wave also, apart from the ratio of amplitude of the modulating wave upon amplitude of the carrier wave. So we move ahead now, and for that, if let's say mu is between the value of mu is between 0 to 1, then there would be a distance. If mu is exactly 1, these 2 points will touch each other, because am minus AC is 0 in that case, mu is 1, am is equal to AC. So these 2 points will touch with each other at the x-axis, and if let's say if I put mu to be greater than 1, then these 2 points will overlap, and this is not required. So if this particular situation is not acceptable, so mu should be, this is the right way to do the modulation. The amplitude of the modulating signal should be less than the amplitude of the carrier signal. Now coming to the bandwidth of the amplitude modulated wave, this is equal to F max minus F minimum, the maximum frequency upon minimum frequency. So we have this particular, this particular equation from the AM. This is my standard equation of amplitude modulated wave. Now I will solve and open the brackets. One component is this one, and another component will be the multiplication of two cosine terms. I will open it. These two angles will be added, and then in the next, the omega, these two frequencies will be subtracted. So when I will open this, I can get, this is my original carrier, as I can see here. This I have taken my original carrier wave. This term is exactly the same, and now this particular term is having the two frequencies to be added. That means it is my upper sideband, okay, and this is my lower sideband, because here I am taking the difference FC minus FM. Here I have FC plus FM. So I have one carrier signal, one upper sideband, and then another one is lower sideband. The amplitude wave has three frequencies now: FC, FC plus FM, and FC minus FM. So F max is FC plus FM, and F minimum is FC minus FM. And now I can calculate the bandwidth. The bandwidth by using this, and we can get the bandwidth to be twice of FM. The bandwidth of the amplitude modulated wave comes out to be of AM wave is 2 FM, right? Now I want to do the power calculation. Since we know only power signals can be transmitted in the air, so it is very, very important to consider the power calculations. So I need to calculate the power of my carrier signal, power of the USP, and power of the LSB. The three powers will constitute to give me the total power content of the amplitude modulated wave. We have this particular equation. So now the power of the carrier wave will be, since the amplitude is AC, I will take the RMS and this square upon R. is the power of the carrier wave. Similarly, AC mu by 2 is my amplitude of the USB. I will take the RMS will square and then divide it by resistance. Power of LSB, again it is AC mu by 2. AC mu by 2, this one. AC mu by 2, the RMS root 2 square upon R. I will add these three to get the total power of my amplitude modulated wave. The power of the carrier, the power of the USB and the power of LSB. Here we can note down the power of carrier, the power of USB and the power of LSB. The power of USB and power of LSB are same. So we can say the power of USB and power of LSB is same. So on solving, take AC square upon 2R to be common. We can get 1 plus mu square by 4 plus mu square by 4. That means at the end we can get PT is equal to PC 1 plus mu square by 2. If I say mu is equal to 1, then PT will equal to the power of AM wave is equal to 1.5 the carrier power. So the power required for transmitting an AM wave is 1.5 times the carrier power for a perfect modulation. Now here we will do one numerical, which is an AM transmitter has a carrier power. This is given as PC. The percentage of modulation is 85%. Mu is 85%. Always note, mu is always lying between 0 to 1. So we will write 0.85 for solving the numerical. Now we have to calculate the total power. PT is equal to PC 1 plus mu square by 2. Put the value of PC. This is 30 watts. 1 plus 0.85 square upon 2, and hence it will come out to be 40.8, right? The next power, the next part in which the question is asking the power of sideband both. So we know that PT is equal to PC plus PUSB plus PLSB. I know total power 40.8 and this is 30 plus PUSB plus PLSB. So PUSB plus PLSB is, this two are equal. So 40.8 minus 30 divided by 2, you can get this 5.4 watts the power in the each sideband. Again coming out to be, here it is in the example 2, it is given that antenna has impedance of R, it is given 40 ohm. Unmodulated AM signal produces a current. That means whenever only carrier is being transmitted, unmodulated carrier, modulating signal cannot be transmitted. So it is talking of the antenna current is 4.8 ampere. The antenna current is 4.8 ampere. So it is talking of I square R, the power of PC. Okay, IC it is given and IC square R is the power of carrier. The power of carrier is given, mu is 0.9. Now we can calculate the PC from this particular formula and it will come out to be 921.6 watts. Now the carrier power, total power we can find out again from the previous formula. PC 1 plus mu square by 2, mu is also given as 0.9 in the example. PC is known, PT is known, PT minus PC divided by 2 will give you power of USB is equal to power of LSB. In this way, you can find out the power of LSB, power of USB, and power of total power and power of carrier. So you can solve the numericals by calculating these powers. We have done two numericals and calculated the amplitude modulation powers in carrier in upper sideband and in lower sideband, and combining all these three we can calculate the total power. And coming to the diagram, we should have mu to be equal to 0, between 0 to 1, and this mu is defined as A max minus A minimum upon A max plus A minimum. And we have understood this particular diagram. The final amplitude modulated wave is this wave. Always remember, this wave is the final amplitude modulated wave. Thank you.